Today, we're going to hear from Martina Chruslinska. She has been working on population synthesis models and with CRISPR genes in particular about what is the measure rate of neutron star binaries and how does that depend on the formalism of common envelope in general. So I just leave it to Martina to elaborate on this for us. And please, Martina, you can start.
Okay. So hello, first, thank you very much for giving me the opportunity to give this talk, and I hope you can hear me well. So as introduced, my name is Martina Chruslinska, and I'm currently a PhD student at the Radboud University in Nijmegen in the Netherlands. And I'm mostly interested in binary evolution, in evolution of massive stars in the context of gravitational wave sources. So I was asked to give a talk about the merger rates of double neutron stars from the population synthesis point of view. So that's what I will do now. And let me start by saying why is it an interesting topic to talk for 40 minutes at all. So first of all, double neutron stars are interesting objects. And if we happen to see their merger in gravitational waves and electromagnetic waves, as we did last year, then it has an impact on different areas of research, ranging from binary evolution, R elements production, short gamma ray burst physics, to even Hubble constant estimation. And for at least a couple of those areas, it is actually important to know how often such mergers happen. So what are the merger rates of double neutron stars? And we need to know this, for instance, to understand whether those events are able to explain the process enrichment of galaxies, or to understand short gamma ray burst physics to constrain the models, and possibly to understand whether the double neutron stars are the only progenitors. But also, comparison of theoretically inferred rates with observations is one of the possible ways to constrain models describing binary evolution. And this is what I'm going to focus on since I'm working on this. So when I'll be referring to merger rate throughout my talk, I actually mean merger rate density. So a number of mergers of two neutron stars happening per unit of time in a certain volume. And if we are interested in local redshifts around 0, then we call this quantity local merger rate density. There are other measures of frequency of mergers, like a rate per Milky Way equivalent galaxy, which is naturally estimated when we look, for instance, on galactic systems. And the detection rate, when we also have to take into account the specification of our detector. So for double neutron stars, so we can get an idea of this number, both from observations and the theory, which in the end gives us this opportunity to compare the two. And if we do that correctly, we can hopefully learn something. And on the observational side, we can use, for instance, we can use different probes to learn about the merger rate, for instance, short gamma ray burst observations, of which we now know that at least some of them are connected to double neutron star mergers. The associated kilonova emission, gravitational waves observations, and also systems known to reside in our galaxy. And here you can see a selection of limits based on different probes on observations. So there is a merger rate density on the vertical axis. And you can see that even a single estimate can gives a range that can span by more than an order of magnitude. So the three leftmost bins, so the green one, yellow, and the blue one are limits based on short gamma ray burst observations. And the reason why this range allowed by observations is so wide, well, one of the reasons, but probably the main, is the weakly constrained jet opening angle of the jet emission from short gamma ray burst. So if this emission is more collimated, then the upper limit is higher. And if it's more isotropic, then the lower limit will go down. And we also don't really know what fraction of those bursts comes from double neutron star mergers. Then the two reddish bins come from estimates based on galactic systems. And the main reason between the two estimates that you can see is the number of systems that was included in the analysis. So the more recent one included more systems, but the sample that we have currently observed is still quite small. So each new observation can affect the range that we see. And also this estimate based on galactic sample is naturally made for a Milky Way-like galaxy. And to put it on this plot, we have to extrapolate to the local volume. So we have to assume something additionally, and this is not a straightforward procedure. You can also see this hatched range in the estimate made by Paul, so the upper part of this estimate. This is actually the more optimistic limit than what was indicated as a fiducial value by the authors, and this comes from changing the assumptions about the luminosity function of pulsars and also trying to account for contribution from elliptical and dwarf galaxies. And finally, there's this purple wide range, which comes from limits based on gravitational waves observations, which were updated a couple of days ago. Well, we only have one detection so far, but this is the most direct probe of double neutron star mergers. To make a theoretical estimate, we usually relate to simulations that allow us to follow the formation of stars within the universe and then trace their evolution and the interaction. And in the end, count the number of systems that formed two neutron stars that are close enough to merge within the Hubble time or in a different, interesting for us time interval. And there are two essentially different formation channels through which we can form double neutron star systems. The first one is isolated channels, where we have two stars in a binary that evolves without any dynamical interaction. So dynamical interactions can be neglected. And the other one does the reverse, so looks at focuses on globular and nuclear clusters where those dynamical interactions are relatively frequent. And it seems that the dynamical channels give a negligible contribution to the overall merging populations of double neutron stars. So those rates were estimated to be around 2 orders of magnitude lower than typical estimates from the isolated channel. However, we don't have really many estimates for double neutron stars from dynamical channels. And during the rest of my talk, I'm going to focus on the isolated evolution. So let's see where these theoretical estimates fall within the figure that I've showed you a couple of slides ago. So you can see now those horizontal lines, which mark results of only some of the recent studies. There's way more. There are way more studies that delivered estimates of double neutron star merger rates over the years. However, these limits that I'm showing you are quite representative in terms of the range of values possible to obtain with the population synthesis studies. So there are solid lines which mark results from most standard models, and the dashed lines show you the most optimistic values obtained in different studies. But the thing that I want you to take from this figure now is that those theoretical estimates also cover a pretty wide range in local merger rates. So to understand why, let me spend a couple of slides now explaining the methods, so how we calculate those rates. So we need a couple of ingredients to do this. And the first one is what I called here a cosmological context. So we have to specify the conditions in which our stars are forming. In particular, for any given time, we need to know how many stars we should form and what are their metallicities. And when we do that, then we have to choose initial parameters of stars or binaries. So first we need to choose a mass of potential primary star from the initial mass function. And then we have to decide whether it should have a companion by setting a binary fraction. And if it has a companion, then we can choose a mass ratio and other binary parameters like separation and eccentricity. And a recent study by Moe and Di Stefano shows that those parameters are likely correlated, so shouldn't be drawn independently from distributions, which was not really accounted for in previous studies. So when we have our binary, then we need to follow evolution of stars and their interaction up to the point where either the binary is destroyed or it forms two neutron stars. And then its evolution is determined by gravitational wave emission. For each given redshift or point in time, we have to loop through those steps 2 and 3 up to the point where we form enough stars to agree with the assumed star formation rate. And then we can repeat the whole procedure, changing redshift, so slowly populating a universe with stars. And in the end, we can count the number of merging systems. So we obtain an estimate of a merger rate given the assumptions that we made. The assumptions that we made during each of those 3 steps, but it's actually common to assume that the population synthesis model is defined by assumptions made only in step 3, so only in the description of the stellar and binary evolution, which is understandable when we take into account the fact that variations in the rate estimate that we get in the end coming from evolutions can be even larger than an order of magnitude, while, for instance, those related to changing the initial the distributions from which we draw initial parameters of binaries in a reasonable range were constrained to affect those estimates by around a factor of 2. However, when it comes to comparison with observations, then we have to take into account the uncertainty related to all of those steps, and in particular step number 1, so our cosmological context, which was not really discussed in previous studies, and I will come back to this later. And for now, let's try to understand what happens during the evolution that those rate estimates can differ so badly due to evolution-related assumptions. So there is an agreement on what phases a binary needs to go through to form a merging double neutron star in the end. And some of those phases can affect the size of the population of our merging double neutron star candidate systems quite significantly. And unfortunately, those phases are also quite weakly constrained by both theory and observations at the moment, which means that if we change the assumptions that we use to describe those phases within the limits allowed by our current understanding, then we can affect the rate estimate a lot. And now let's have a quick look at this typical evolutionary scenario for a formation of merging double neutron star to identify those phases. So since we need to form a merging system, a very close binary in the end, then sooner or later when our stars evolve, one of the companions will overfill its Roche loop and start the interaction, so mass transfer. And we don't really know well how much mass is lost from the system during such interaction, neither how much angular momentum is carried away with the escaping matter. And this is important to know what is the separation and mass of the accretor after that interaction. And then since we need to form two neutron stars, so we need two core collapse events, most likely supernovae explosions. And we know from observations that neutron stars gain velocities at their formation, since they are faster than their parent population. And observations of young and single pulsars suggest that those velocities are around of the order of a couple hundreds of kilometers per second, which is enough to disrupt the orbit, disrupt the binary, especially at the formation of first neutron star, when the orbit is still wide. And at the same time, the double neutron star systems that we observe, well, at least some of them, should have formed with small natal kicks, like a couple of tens kilometers per second. Otherwise, we have problems with explaining their parameters. We also observe pulsars in globular clusters that have escape velocities of around 50 kilometers per second, which means that at least some neutron stars should form with lower natal kicks. But as long as we don't have good constraints on this velocity distribution, this phase of formation of neutron star is one of the bottlenecks involved in our calculations or in models of stellar evolution. And then comes the real bottleneck involved in our model, because neutron star progenitors expand during their evolution, reaching sizes of hundreds to even thousands solar radii. And in the end, to have a double neutron star system that will merge within a Hubble time, we need to have a separation of a solar radius or less, which means that we need to have an efficient mechanism to decrease the orbital separation of a couple of orders of magnitude. And within the classical binary evolution channel, this mechanism is provided by common envelope, which is a short-lived phase that happens when we have a really high mass transfer rate, so it goes unstable. The accretor cannot accommodate all of the material, and this material starts to fill the binary, and effectively a star and the donor's core are immersed in a shared envelope, and they orbit within this material, which causes stars to experience an enhanced friction, and they start to spiral inwards. Now, we don't want them to spiral in too much, because they will merge and will not form a double neutron star binary. So binary, at least in some, the envelope, at least in some cases, has to be ejected. And this can happen at the expense of the orbital energy, and probably with the help of some other energy sources. But we don't really know what are the exact conditions for the occurrence of common envelope, nor for its ejection. And there is also a distinguished controversial case where the donor star does not have a well-defined boundary between the core and the envelope. As for instance happens when a star evolves of the main sequence to become a giant. And then some studies suggest that such a common envelope should always lead to merger, where there are some studies which suggest that in some cases where we usually assume that the common envelope proceeds, the mass transfer should be stable. So this is one of the unknown factors in the evolution. And finally, it also matters, especially for the most massive star, what we assume about the wind mass loss. So this is mostly important for black hole progenitors and can affect the mass of a star a lot. And I'm showing you now the example results of a parameter study that focused on looking at how the assumptions that we make throughout the stages that are just discussed about the evolution affect the rate estimate for double neutron star systems. So this is pretty busy, and you can check out the details in the paper, and for now let me simplify this a bit. So on the vertical axis you can see the local merger rate density again, And then on the horizontal, there are some labels which indicate the models, so assumptions about the evolution that were varied with respect to the reference model. And each of the models comes into variation, indicated by red and blue points. So those two colors distinguish the assumption made about this controversial common envelope case that I just described. So in the red case, we allowed the common envelope in this case to proceed, while in the blue, we assumed that this phase always leads to merger. So the rates are higher in the red case, and you can see that this is quite important what we assume this for the final estimate. Now we can further increase the rates if we assume, for instance, that the natal kicks obtained by neutron stars at formation are lower, changing some assumptions about the mass transfer or combining several of those factors. And you can see now some most optimistic estimates made by other groups. So this horizontal green line shows the estimate by Mappelli and Jacobo. So they assumed here that all of the neutron stars form with low natal kicks, and they also they also assumed high common envelope efficiency, which parameterizes the ease with which you can eject the envelope. Those factors were also varied in some earlier studies, and they are known to affect the rate estimates substantially. And this is the estimate by Eldridge and others. So they used their new model, the updated model by Braid and Eldridge, which describes the natal kicks that neutron stars receive. So in their model, the magnitude of this velocity depends on the amount of mass that is ejected during the supernova and also on the mass of the remnant. While in most cases, people assume that this velocity is independent of properties of the star that undergoes a supernova. And the important thing is that in binaries, if this model is used, the natal kicks are usually lower than if you assume that they are not related to properties of the exploding star. So to summarize this part, most of the standard assumptions about the binary evolution lead to estimated merger rates indicated by those solid lines here, which fall short of neutron star mergers when we contrast this with most of the observational limits. And within the standard evolutionary scenario for the formation of double neutron stars, merging double neutron stars, there are some factors that largely affect the estimates, which are natal kicks and common envelope evolution. So models with low natal kicks and with specific assumptions about the common envelope can reach to high rate values that are close to the most the best estimate made based on the detection of gravitational waves from emerging neutron stars. So does it mean that that this is the correct description of the evolution? Well, not necessarily, because those solutions are degenerate. So people focus mostly on the extreme changes, varying one assumption at the time. But we can also make several more moderate modifications to our assumption and reach a similar estimate. So it's important to use also other constraints, not only merger rates, to disentangle. And still, I didn't say a word, for instance, on the importance of the assumptions related to step one. So going back to this slide, to the assumptions about the star formation rate, cosmic star formation rate, and metallicity. So why should this be important at all? Well, because a binary that forms at a certain moment in time, it forms with a metallicity that is typical for its neighborhood at that time. And then it needs a certain time to evolve to form two neutron stars, which then slowly decrease the orbital separation due to gravitational wave emission. And this delay time depends on the parameters of the binary. And since double compact objects can form with different parameters, then different binaries formed at different times with different metallicities will, in the end, all contribute to the merger rate we measure at some point. Now, metallicity is very important here because it affects the stellar and binary evolution a lot. For instance, stellar wind mass loss is known to depend on metallicity. And to form massive black holes as those detected by LIGO, so like half of the detections was suggested that those black holes were quite massive. And to explain their formation, we need to go to low metallicities. Otherwise, we lose so much mass during evolution that we cannot form such a massive black hole. But this is not only winds are affected by metallicity. For instance, radius evolution is different at the different metallicities, which means for binaries in particular that if we have two binaries with the same parameters but different metallicities, then they can start interaction at different moments during the evolution, and the outcome of this evolution can be different. So since binary evolution depends on metallicity, also the efficiency of formation of merging double compact objects will depend on metallicity. Which means that what we really need to know is how is the cosmic star formation distributed at different metallicities. Not only how many stars are forming at a certain moment, but also at what metallicities. And then we can ask several questions. So particularly relevant is how does this distribution look like and how uncertain is it? And finally, how important is it for the final result, for the rate estimate? So what I'm showing now is a number of merging binaries, double compact objects that form per unit of star forming mass as a function of metallicity. So, and looking at the blue line, which corresponds to double black holes, you can clearly see that metallicity is an important factor here. Because there are way less double black holes, merging double black holes forming at metallicity around solar than, say, 10% solar value, which is not the case for the red curve, which corresponds to double neutron stars. So it shows that if we change the assumptions about how is the cosmic star formation rate distributed at metallicities, then this will affect the merger rates of different types of double compact objects differently. And now if you try hard, then maybe you can see those thin lines that appeared in the background. So they show the same relation, but for different model. So for different set of assumptions about the binary evolution. And now it doesn't matter what assumptions exactly, I just want to show that in general, this is model dependent. But there are several features that appear robust. So, for instance, if more star formation happens at high metallicities than what we assume, then double black hole merger rates should be lower, and those of double neutron stars probably a bit higher. So how does this distribution look like? Well, at least within the population synthesis community, there seems to be no definitive answer to that question, because different groups took different approaches to extract this information, ranging from using cosmological simulations to looking at observations of star-forming galaxies. And I would like to contrast two of those assumptions now. So those described in the papers that I'm highlighting now. I will keep the assumptions about the star formation rate the same and only change the way it's divided between metallicities. So I'm simplifying things a bit, but the method by Dominic is based on average metallicity of galaxies, while the one by Belczynski is based on average metallicity of the universe, which to take into account that this is not really the metallicity at which star formation happens, was increased by 0.5x. So here I'm showing you the redshift evolution of mean metallicity in both cases, so those thick lines. And I assume that the scatter around this mean is the same in both cases. And you can see, for instance, that to guide you a bit, I indicated where there is solar metallicity and 10% solar fall in this figure. So you can see that at redshift 0 in the blue case, the mean metallicity is more or less solar, while it's never reaching to solar value in the red case. And here you can see on the left now, there appeared a distribution of metallicities at which stars were forming in both cases since redshift of 10. And the hatched region of this distribution shows the star formation at metallicities below 10% solar, which I consider low. So you can see that the fraction of low metallicity star formation is quite different in both cases. So how going from red universe to the blue one would affect the rate estimates? You can see that here. Let me spend a moment describing this figure to make it more familiar, because there are many things here. So on the vertical axis, again, there is a local merger rate density. And there are two climbs of points, which correspond to two different models, so assumptions about the evolution. And then those clumps are contained within thick bins of two colors, which corresponds to two different ways to divide the cosmic star formation rate between metallicities that were used to calculate the rates. So our blue and red example. And different symbols correspond to different types of double compact objects. So black holes are black here. The purple diamonds are double neutron star systems, and the mixed systems are indicated in green. And there are also limits, observational limits made based on gravitational wave observations. And you can also see some kind of error bars, which indicate how much the estimate would change if I would use different distributions of initial parameters for binaries. So changing to more recent one would basically decrease the estimate by a factor of 2. So we can basically repeat the conclusions that we've already reached looking at the number of double compact objects forming at different metallicities as a function of metallicity. So we can, for instance, see that if there is more star formation at high metallicity, so comparing the red and blue, then we are talking about blue, in which more star formation happens at high metallicities. The local merger rates of double black holes would decrease, while those for double neutron stars would increase a bit. But looking at the right part of this figure, you can also see that if we would like to compare with observations, then we would reach slightly different conclusions from the red universe and blue, because in the red case, we would conclude that we are overestimating the number of merging double black holes. So maybe our model is wrong, or maybe we should change the assumptions about the evolution for more massive stars, for instance. So maybe black holes should form with larger natal kicks, or maybe the common envelope evolution is different for more massive stars. But in the blue case, we can match these observational limits for all types of double compact objects for the same set of assumptions, which is a bit worrying and only highlights the need to be more careful when we choose the distribution of the cosmic star formation at metallicities, and we need to understand the associated uncertainties. Which brings me to my current project. So I'm trying to see what we can learn about this distribution by looking at the observational properties of star-forming galaxies. And in particular, I would like to see how different this distribution can be within the limits that are allowed by those observations. And as a preliminary attempt to answer the question, how uncertain is it, how different it can be, I'm showing you the two distributions which correspond to two extreme cases that I find based on those observational properties of local star-forming galaxies. So these are the distributions of metallicities at which stars were forming since redshift of 0.5. And one way to compare them is to, for instance, look at the fraction of stars of stellar mass that formed at low metallicity, so below 10% stellar, which for these two cases that I'm showing now is between 2 to 11%. And we can contrast this with our just discussed example of the red and blue case. So in blue case, this would be 4%, this low metallicity star formation, while in the red case, it would be 24, which, well, so based on observational properties of star-forming galaxies, we would conclude that in the red version of the universe, we were overestimating the low metallicity star formation. And the last thing before I stop talking that I wanted to mention is not about the merger rate itself, but something closely related. So about the delay time, because population synthesis studies usually find that this delay time distribution is strongly peaked at short merger times. Maybe not as short as people working ultra-fine dwarf galaxies would need to understand our process enrichment, but still something like a couple of tens to hundreds of mega years, which means that we would expect to see double neutron star mergers mostly in young stellar populations, actively star-forming galaxies. And we saw the only so far detected gravitational waves from merging double neutron stars in elliptical galaxy, with limits on star formation suggesting that there was little to no star formation during the last 2 gigayears, which is a bit surprising. And this was only to highlight that well, even if we can understand the high merger rate implied by gravitational wave observations within our standard evolutionary scenario for the formation of a merging double neutron star, there are still some elements that don't quite match, and there's still work to be done. So to summarize, I first discussed briefly observational estimates of double neutron star merger rates, which deliver a pretty wide range due to selection effects, things like beaming, luminosity function, and small sample. And then I moved on to theoretical estimates, which again deliver a pretty wide range of estimates due to some other things, mostly uncertain factors involved in the evolution of binaries. For double neutron stars, this most important are natal kicks and common envelope. And I stressed that those solutions are degenerate, and we need to use also other observational constraints. And then I discussed the importance of what we assume about the star formation history and chemical evolution of the universe for the rate estimates. I stressed that metallicity is important for stellar evolution, and showed you that there are different approaches taken by different groups. They are making different assumptions, and this gives different rates estimates, and in some extreme cases can even lead to different conclusions when we compare with the observations. So we need to have a reasonable picture of the division of the star formation at different metallicities of this distribution. And we need to understand the uncertainties, so how different, how much this distribution can differ within the uncertainty limits. And finally, I mentioned the delay time distribution that suggests that we expect to see double neutron star mergers in young stellar populations, rather than in NGC 4993 when we saw GW 170817. Yes, thank you. Thank you for listening.
So if you have any question, you can either write it in the chat or just unmute yourself and ask the question. I can start asking questions. If you go back to a few of the slides from your last slide showing the red and blue comparison for black hole merger rate and neutron star merger rate.
This one?
Yes, so going from red to, so I should be looking at the rightmost two bars, right?
Yes.
And then going from red to blue, it says that the measure rate of the neutron stars increase, but for the black holes decrease.
Yes.
And what I should be looking, should I compare to so the black hole measure rate, it's better to be lower because it's closer to the limit?
Yes, so current limits from gravitational waves for black holes are indicated in black. So to agree with those estimates, for us it's better if we are in the blue universe or something close to.
Where is the limit for the neutron star?
So the neutron star is this purple range. So it's yeah, everything colored, and it goes even higher.
So then the blue is more compatible with the observations, no?
Yes.
Okay. I thought that you have been mentioning that both have problems either way, but it sounds like one of them is more consistent with both the black hole rays and neutron star measure rates.
Yeah, yes, so maybe I went through this too quickly, but what I meant here is exactly this. So if we look at the red bin, I'm not sure if you can see the cursor now.
Yes.
Okay, great. So here you can see that even within this error bar, which indicates the uncertainty due to assumed initial distribution, we are above the limit implied by gravitational wave observations for double black holes. So, but if we change this distribution of star formation at metallicities to the one that assumed that this mean metallicity should be higher, then this agrees with the limits, right? So it's maybe better, maybe more true in some sense.
And what is the difference between the treatment of the common envelope in this model compared to the reference model?
So the difference between the common envelope treatment between those two models is that in the reference model, this is the pessimistic case. So in this case where we have a Hertzsprung gap like donor star, we assume that it always leads to merger. So we basically have less systems surviving common envelope, while in the model, this model, this common envelope was allowed. So more systems survived this stage.
And do they also stage the case BB as an unstable phase, or is it just when the hydrogen is being destroyed?
Yes, so yeah, so this can also be within this model. So within it can be initiated by the donor star that is within what we assume a Hertzsprung gap-like donor. So the star that does not have this clear distinction between core and the envelope.
I've asked my questions. If anybody has any question, please unmute. Otherwise, I guess we will see you guys in 2 weeks with a talk about nuclear R process science. And I'm again thankful to Martina to connect in, I guess it's, I don't know what time it is in Europe, but thank you for, for joining us.
Friday evening.
Thank you so much. So I will say goodbye and see you in 2 weeks.